Hello.
Hi everyone, I'm Chatu, and today I will present to you part of my PhD project on where we assessed two lakes with varying trophic or nutrient status to effects of increasing temperatures and nutrient loading. So to start off with, I'll give a little bit of background on the potential issues and talk about the method and the analysis we used and present some of the results from the study. Sorry. Okay, so eutrophication or enrichment of nutrients in freshwater systems is a common problem that's faced by many lakes and reservoirs from around the world. And one of the main consequences of eutrophication is the development of nuisance algal blooms, and most of these algal blooms could be dominated by cyanobacteria. And cyanobacterial blooms are undesirable because they can produce toxins like hepatotoxins and neurotoxins that affect the liver and the nervous systems. And studies have also shown that these toxins could actually be even more poisonous than cobra venom. So it's a pretty big thing. And cyanobacteria can also produce chemical compounds that change the color, the taste, and the odor of water. So all of these incur very high economic costs. Studies have shown economical costs associated with cyanobacterial blooms to be around $180 to $200 million per annum. It has been predicted that these algal blooms would increase with increasing temperatures associated with global warming. Many parts of the world have been experiencing increasing temperatures, and some parts of the world have experienced a greater degree in change than the other parts of the world. IPCC has predicted a temperature increase of about 1.7 to 4.8 degrees by 2100 under the worst case emission scenario. So this is what typically occurs in an aquatic system when the temperatures increase. So increasing air temperatures would result in the water temperatures to increase, and consequently the water body will stratify due to the strong temperature gradient between the surface waters and the bottom waters. And weak mixing would mean that there's less oxygen being transferred into the bottom waters. So the hypolimnium, or the bottom waters, become pretty anoxic, and these anoxic conditions would result in nutrients being released back into the water column. So nutrients such as phosphorus, not just nutrients, but also heavy metals like manganese and iron will be released back into the water column. So this aggravates the eutrophication problem because you have these external nutrients coming in from the catchment due to land use changes or land use modifications, and then there's also this internal nutrient loading that's aggravating the eutrophication problem. And also at the same time you get cyanobacterial species that possess physiological adaptations to thrive under such conditions. For example, they have a gas vacuole which allows them to maintain their buoyancy within the water column, so they can access the nutrients at the bottom of the lake and come back up to access light. So what we did was, for our study, we used a one-dimensional hydrodynamic model coupled with the framework for aquatic biogeochemical modeling, which is a biogeochemical model that can determine, in order to determine the responses of two different lakes, an oligotrophic lake and an eutrophic lake, to increasing temperatures under climate change and to varying nutrient loading scenarios. So for the purpose of the study, we used Lake Tarawera from New Zealand, which is an oligotrophic lake, and also Mount Bull Reservoir from South Australia, which is an eutrophic reservoir. So just to give a little bit of background on the model that we use, the general lake model is a framework under a bigger model called the aquatic ecodynamic model, and it is a It is an open source free model that's developed by the University of Western Australia. It can be used to reproduce vertical profiles of temperature, salinity, and density. It uses the commonly used Lagrangian layer structure, which takes into account information such as meteorological inflows and outflows to adjust the layer thickness by expanding and contracting. And the GLM is then coupled with the biogeochemical framework, which is the FABM. It's a set of codes that can be used to compute nutrients such as nitrogen, carbon, phosphorus, silica in all sorts of forms, particulate, dissolved, inorganic, and organic. It can also use to simulate phytoplankton groups and zooplankton groups by defining their growth rates, nutrient uptake rates, and optimal light, nutrient conditions among various other parameters. For the purpose of this model, we simulated 3 common phytoplankton groups consisting of cyanobacteria, diatoms, and chlorophytes. And we used a general parameter set to represent the phytoplankton species observed in both of the lakes, in Lake Tarawera and Mount Board. Although this might not be the reality, we had to do this so that we can compare the results at the end, and the results would be independent of the parameters that we used. So just a bit of site description. Mount Bold is, Lake Tarawera is from New Zealand, and it's part of the Rotorua Lakes in the northern New Zealand. It's a very clear, deep lake, has a maximum depth of about 88 meters. It has a catchment that's predominantly consisting of native forest, very pristine, but lately they've been observing rare occasions of cyanobacterial proliferation. And you can see that it's the low nutrient status by the mean summer chlorophyll, the very low mean summer chlorophyll values of about 1.3 micrograms per liter. And Mount Bull Reservoir, the South Australian reservoir, it has about 47 meters, maximum depth of 47 meters under its full capacity. It is an eutrophic reservoir and has very turbid waters. It receives water predominantly from a catchment that's consisting of agricultural land. The mean summer chlorophyll values are about 10 micrograms per liter. So we calibrated the model for about 2 years, starting from 2003 to 2004, and validated it for a period of 1 to 1.5 years, depending on data availability. So the next thing was to observe to check the observed values and the modeled values so that we can get an idea of the performance of the model. The goodness of fit measures, or how the model performance, was calculated by using root mean square error and the coefficient of determination, which is the R square value. So as you can see, this is an example of the temperature profiles for Tarawera. The model was able to capture mixing events and stratifications events pretty well. And also the R square values are close to 1, which means it's a good fit. And then we have the temperature profiles for Mount Board, which is again, we saw very good goodness of fit, because it was again able to capture the events of stratification and mixing pretty well. We also compared our goodness of fit measures with the other variables such as nutrients and phytoplankton, using the literature values, what they got for other studies that they've been conducting using similar models, and our values seem very comparable and sometimes better and almost similar. So this gave us the confidence to go ahead with the scenario analysis. Oh, this is for the calibration for Mount Bold. Scenarios were constructed by changing the nutrient loading, so we increased and decreased the nutrient loads by 10 folds and 20 folds. This was just to get a change in the trophic status, because the main purpose of this study was to understand how the trophic status affected the phytoplankton composition and abundance. So we had to increase them by 10-20 folds and decrease by 10-20 folds in order to get a shift in the trophic status. And we also increased the temperatures by 1 to 4 degrees as guided by the IPCC projections. Just to give an idea of the responses compared to the anti-different nutrients in relation to the total chlorophyll or the algal biomass. To the left you have Lake Tarawera. As you can see, the top left is when, let me introduce this. Top left is the Tarawera under no nutrient increase or decrease, which is its oligotrophic state. And you can see under increasing temperatures, it didn't really increase or have a significant impact on the overall or the average total chlorophyll. It just shifted the summer peak forward. Whereas Mount Bold, under increasing temperatures, under its original trophic state, which is the eutrophic state, it sort of doubled the algal biomass. And considering the hyper-eutrophic lake, when the nutrient status of the Lake Tarawera was changed from oligotrophic to hyper-eutrophic, under increasing temperatures, it tripled, or the algal biomass increased by 3 folds. And for Mount Bold, when the nutrients increased, again, as expected, it increased the total phytoplankton concentrations, and decrease in nutrients resulted in decreased phytoplankton biomass. And quickly going through the percentage of phytoplankton composition in both of the lakes, we're starting off with the lake that's with cyanobacteria, chlorophytes, and diatoms. With increasing nutrients, we did not see an increase in cyanobacterial composition, but instead chlorophytes dominated. Cyanobacteria was only dominant when the nutrients were low. For Mount Bold, we did not see a change in the phytoplankton composition. The phytoplankton was dominated by chlorophytes. And this is not surprising given the physiological adaptations of chlorophytes and cyanobacteria, because chlorophytes have very high growth rates and nutrient uptake rates, and they also can grow in a wide range of temperatures. Cyanobacteria, because they have low nutrient uptake rates and very good nutrient storage, they can thrive under low nutrient conditions. So what happens with increasing temperatures is that usually it increases the metabolic rates of living cells, such as it increases the growth rates and respiration rate, and nutrient uptake rates. And this would mean that the biological demand for nutrients is increased under increasing temperatures. So when the nutrients are available and the temperatures are high, it will accelerate the nutrient uptake and grow faster. So the temperature influence can be significantly enhanced by the availability of nutrients. Sorry, I'm running out of time. The key findings from this study would be that there's an increasing chlorophyll concentration under increasing temperatures and nutrients in Tarawera and Mount Bold. And there was a change in phytoplankton composition in Tarawera, where the composition was dominated by chlorophytes, and we saw that the reduction in nutrients prevented the excessive phytoplankton growth, which otherwise could have occurred under increasing temperatures. So we can say that nutrient poor or oligotrophic lakes are resilient to impacts of nutrients and impacts of temperature than eutrophic or hyper-eutrophic lakes. Putting this into management perspective, Although we didn't see an increase in cyanobacterial dominance, this does not mean that there'll be no nuisance algal blooms. It will be there, and this will affect the water treatment processes and also affect the aquatic habitats by blocking gills of fish. And we argue that catchment and land managers have the potential or the opportunity to offset some of the negative impacts of climate change by effective land use management. And failure to reduce nutrient loadings or failure to act on this or reduce the nutrients to the waterways would mean that traditional lake restoration techniques like alum dosing or copper sulfate dosing or use of a mixer would have to be done at a higher intensity for a longer period of time. Okay.